Hello chemists, this is Miss Placino and you are watching Screencast 2.5 on quantum mechanical electron configuration. Hopefully from the last couple of screencasts that we've done, you've really been able to take away the idea that the behavior of the electron is bizarre, and it was completely unexpected to the physicists who were studying it in the early 1900s. So they couldn't describe the behavior using the Bohr model, so they changed it to the quantum mechanical model, and in the previous lesson we talked about the different energy levels, sublevels, and orbitals that exist within this model of the atom. Today we're really going to focus on how the electrons are going to fill the different energy levels and sublevels. Before we do that, let's take a look at the do now. How are the Bohr model of the atom and the quantum mechanical model of the atom the same? How are they different? So pause the video, see if you can come up with maybe 2 or 3 different similarities and differences for this problem. Okay, so I've come up with my list for similarities or things that are the same between the two models. In both cases, the nucleus is treated more or less identically. They don't know about the neutrons just yet, but from Rutherford's gold foil experiment, we know that the nucleus is a small, positively charged, dense mass at the center of the atom. Both of these models of the atom take into consideration that energy is quantized. In other words, there are rules about where the electrons can exist. And both of these models assume that the electrons are in constant random motion. There are some very important key differences between the two models. I've got these 3. The Bohr model looked at electrons traveling in paths. I think about that with the nucleus at the center, and then we just got the electron orbits. And the electrons kind of move around the nucleus in those well-defined paths, whereas in the quantum mechanical model, we talk more about clouds. Also, in the Bohr model, we know where the electrons are at any given point in time. In the quantum mechanical model, due to the Heisenberg uncertainty principle, we talk about the probability of finding an electron. And I guess it probably is stated in the other two, but the Bohr model of the atom was really simple, both from a conceptual perspective as well as a mathematical perspective. And hopefully you learned yesterday that the quantum mechanical model of the atom is very complex, both conceptually and mathematically. For this class, we're going to stay away from the mathematical aspect of the quantum mechanical model, and we're just really going to focus on the conceptual stuff. So let's get into that now. The quantum mechanical model and trying to fill your electrons into the different energy levels and sublevels is all about the Aufbau principle. And all the Aufbau principle states is that electrons must fill the lowest energy levels first. And if you think back to the Bohr model of the atom, Bohr said essentially the same thing. We start with the orbits that were closest to the nucleus. We put electrons in there first, and as those fill up, we gradually move further and further away from the nucleus to larger orbits that are more energetic. Since we've got all those weird shapes with the quantum mechanical model, think about it, we've got our nucleus at the center, then we've got the 1s, the 2s, the 2p, and there's 3 different 2p's a little farther out. Then we've got the 3s, and then the 3p, don't mind my drawings, and the 4s, then we got the 3ds, which start getting crazy. We have a lot of what's called orbital overlap, so it's a little bit more involved trying to predict which ones are lowest energy levels first. But we have a tool that you can use to help you out. This is sometimes called a filling table. And we start up at the top at the 1s, and we move down to the 7s, and as you move down that chart, you're going to see increasing energy. I didn't really leave myself a lot of space, but you see what I mean. So in your workbook, you can follow along. What you want to do is just draw arrows. So I'm going to label that first arrow 1. The second arrow I'll label 2, 3, 4, 5, so on and so forth. And I'm going to follow the arrows. So I'll start with arrow 1, and this is telling me that my first energy level and sublevel that gets filled is the 1s. That's lowest in energy. I've got nowhere else to go with this arrow. So I go to the second arrow. I see the 2s. That has nothing else left to go on. Follow that third arrow. I see 2p and then 3s. And it's finished. Go up to the fourth arrow. I see 3p and then 4s. This is really where we start to get that orbital overlap kicking in. If you move over to arrow 5, you see 3d, then the 4p, then the 5s. So take a moment, pause the video, see if you can go through and take care of the next couple of arrows and get down to the 7s. We'll go there. So you can see that I finished filling out the sublevels and energy levels according to the off-bar principle. We left off at 5s. I picked up with arrow 6, then I go 4d, 5p, 6s, then that one's finished. Then I go to 4f, 5d, oh, I made a mistake. That should say 6p, and then 7s, so on and so forth. It's very rare that you'll need to get to quite this many sublevels and energy levels for most of the problems that we do, but it's really easy for you just to recreate this filling chart on something like a quiz or a test, and this way you can predict how the electrons are going to fill the energy levels and sublevels. So let's try out a practice problem. Let's apply what we've just talked about. So it's telling us to write the quantum mechanical electron configuration for Na. Na is, of course, sodium. And if you were to check the periodic table, you'd see that sodium has 11 electrons. So our job is going to be to use that filling chart, what you just copy down into your notes, to predict where the electrons in a sodium atom are going to occupy as far as the energy level and sublevel. So we know that 1s is the lowest energy level, and I know, actually let me give myself a little more space, 1s, and I know that I can fit a total of 2 electrons into the 1s sublevel. If you think about it, a 1s is just a sphere, and every orbital can hold up to 2 electrons, so the entire 1s energy level and sublevel can hold 2 electrons. I go on to 2s, a little bit bigger but the same shape. It can also hold a total of 2 electrons. I get to my 2p's. I know that there are 3 p orbitals. Each of them can hold a total of 2 electrons, so that gives the p sublevel the ability to hold 6 electrons. Let's max that out at 6. You want to go back and check. I see 2 plus 2 plus 6. That gives me 10 electrons, so I have 1 more electron to account for. And based on the filling chart and the off-bar principle, I have to put that electron into the 3s sublevel. And there's only 1 electron to put in there, so I put 1 like that. We got same thing, an s orbital, just bigger than the 1s and the 2s. So just to remind you, that coefficient is our principal energy level. The s's and the p's are telling us the sublevel. The s's and p's tell us the sublevel that the electrons are in, and that's going to give us some insight into how many electrons can fit. For example, the s can hold 2, the p can hold a total of 6, d's can hold 10, and the f sublevel can hold 14. Finally, we've got this superscript. The superscript is telling us specifically the number of electrons held within that energy level and sublevel. So in this case, we have just the 1 electron in the 3s sublevel. Let's work on some practice problems with this concept. I'm going to quickly recreate a filling chart just so you can see how I do it. I go like 1, 2, 3, 4, 5. I know those are all going to be s's. Go 2p, 3p, 4p, 5p. Then I know that I get to the d's, 3d, 4d, 5d. And then I know that I have the f sublevel starting with the 4th principal energy level. Let's change fonts. Oops, I forgot the s. And just go through and draw my arrows. It's a little misleading, that one. So I know what the order is going to be, and hopefully that'll help me out. I would say when you go to take your test, if you're feeling a little unconfident, just draw this right off the bat. I'm going to walk through iron with you. Just in case you're still a little confused from sodium, then you should pause the video and let's try to get through try these 3 on your own. So again, first thing I do is check the periodic table and see how many electrons I'm working with. With something like iron, I got 26 electrons. And you know what, maybe I won't write that there just so I've got plenty of space. 26 electrons. If I use my filling chart, I know I start with a 1s, so I've got 1s, 2, 2s, 2, 2p, 6, that's 10 electrons, 2 plus 2 plus 6 gives us 10. Then I go to 3s, 2, 3p6. Let's keep following along. 4s2. So if I kept track of my math right, that's 20 electrons that I have so far. And then from the 4s, the next one I get is to the 3d. And I've got 20 electrons accounted for, so that so I know I only need 6 in the 3d sublevel. Go ahead, pause the video. I'm going to go through the practice problems too, but see what you can do. Try to write these full quantum mechanical electron configurations. So I walked through and I finished questions B, C, and D. They all start out the same way, that 1s2, 2s2, 2p6, 3s2, so on and so forth. And it's just really a matter of using your filling chart and keeping track of the electrons and making sure that you're not adding too many or too few per each sublevel. So if you need to, pause the video and check your work. If you look back at your notes, you've got this blank periodic table, and I want to just start filling some stuff out. I'm going to go 1s, 1, and over here 1s2. And from 1s it goes 2s1, 2s2. I would fill up that sublevel. Then we have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Oh. Hopefully you see that a pattern is really going to develop. Don't worry, I'm not going to fill out the whole table. 3p5, 3p6, then I get into the 4s1, 4s2, and I have the D block. I'd see 3d1, 3d2, I bet you could guess how many blocks are going to be here. 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Awesome. This F block at the bottom, we'd see 4f1. Guess how many different blocks we're going to see here? If you're thinking 14, you are correct. It's not coincidental that the periodic table really lines up this way. So you'll hear sometimes people call this far left two columns the S block because all of the valence electrons are in the S sublevel. The P block, as you might be able to guess, is over here where all the P's are. Our D block is in green, that's where the D sublevel is. And our F block is in that yellowish color, and that's where all the elements that contain F electrons are going to exist. When we're talking about different elements or atoms, we're talking about their electrons. One thing that we're really concerned about are valence electrons. And you might remember this term from other classes in the past, but your valence electrons are the ones that are furthest away from the nucleus. We haven't talked much about chemical reactions at this point in time. We'll do that a little bit later this semester, but it's the valence electrons that are the most reactive, and for lack of a better way to describe it at this point in time, the valence electrons give the elements really their different personalities. Are they really reactive? Are they rather inert or non-reactive? Are they going to react aggressively? It's all about valence electrons. Generally speaking, your valence electrons are the last ones that you write, with the exception of our D block, really. Interestingly enough, elements in the D block still keep their valence electrons in the S block, even if the D block is the last one that is written. The way scientists figured this out is they start to ionize different atoms. In other words, they start removing electrons from atoms. And they were able to discover that the like 4s electrons would get lost before the 3d electrons were touched. So they were able to conclude that the 4s electrons are technically the valence electrons. So it's just something to keep in the back of your head. And if you look back at the practice problems, you can see you're being asked to circle valence electrons. So let's do that now. Okay, so we're going to circle our valence electrons, and they're the ones that are going to be farthest away from the nucleus, so the last ones we write, unless they're in the D sublevel. In that case, we're going to go back to the nearest S. So if you take a look at iron, we see the last thing we wrote was 3d6, but since it's a D sublevel, we're going to backtrack to the nearest S sublevel. With strontium, nope, They're just the last ones we wrote since they're in the S sublevel. Same thing with sulfur. Last ones we wrote, it's in the P sublevel. And same thing for krypton. So just be aware that those are where the valence electrons are. We'll focus mostly on the S and P blocks, so it's always going to be the last electrons, especially when we start talking about chemical reactivity. While I've got you looking at your practice problems, there's one more thing I'd just like to point out. If you take a look at those last electrons that we wrote, for example, in iron 3d6, strontium 5s2, sulfur 3p4, and krypton 4p6. And then you look back at the periodic table that we were filling in, and if you can, also look at where those elements are located on the periodic table. You're going to see something kind of cool. So let's do that now. This is where iron is on the periodic table, 3d6. Sulfur, 4p4. I'll have it written there. Krypton is 4p6. And strontium is 5s2. So this is another way that you can predict electron configuration without having to recreate that filling chart. Most students find that they like one way better than the other, and really what you choose to use is completely up to you. As long as you can get to the correct quantum mechanical electron configuration, I'm pretty happy about it. So again, find what works for you, but I think it's a really neat correlation between what the valence electrons are or the last electrons. We know in the case of the D block that the Ds are not the valence electrons, but it matches up to where they're located on the periodic table. We've got one shortcut that I want to show you, and we'll wrap up the lesson on that. Now, everybody likes a shortcut. If you look at your practice problems, you probably saw that you were writing the same things a lot. 1s2, 2s2, 2p6, so on and so forth, and that gets a little monotonous. It's really at the end of the electron configuration where things are potentially interesting. So I want to show you a big shortcut for writing the electron configuration of a quantum mechanical model. So let's look at something like manganese. If you find that on the periodic table, manganese is element 25, and its electron configuration would look something like this. We can shorten that dramatically. What you do is you go back to the nearest noble gas. Get my red pen back. The nearest noble gas is going to be the last P sublevel that's completely filled. In this case, 3p6. If you think about where 3p6 is on the periodic table, kind of using that little trick that we just showed you with the periodic table, you'd see that its valence electrons, or its last electrons, are in the third energy level, the P sublevel. So we're full up to here. So we put argon in brackets, and then we just write out the remainder of the electron configuration. Let's try another one. Phosphorus. We write out the whole configuration. We want to go back to the last filled P sublevel. Looks like it's going to be 2p6. If you check the periodic table, that corresponds to neon. So we can just cut off those first three and just write the Ne in brackets, 3s2, 3p6. Rubidium. Really big atom, whole lots of stuff to fill out. Go ahead and try this one yourself. Pause the video. Okay, hopefully you noticed that this is my last filled P sublevel. That corresponds to krypton. And look at how much I was able to shorten off of the electron configuration. This method is really helpful for those of you who choose to use the periodic table technique. Students who use the filling chart often feel like, well, I have to write all this stuff out anyway, so why would I bother condensing it later? But again, how you choose to solve these problems are really up to you. We're going to be building on this more tomorrow. So I'd say if you could, keep on practicing. I know there's a bunch of extra practice problems in your workbook, and you're going to get better at it. So don't feel too stressed out or upset with yourself if this doesn't come naturally. This is kind of weird, and it does take some practice. All right, hope this was helpful, and I'll see you again soon.